Bismillahirrahmanirrahim. Okay guys, welcome to the synchronous machine part 2 synchronous motor. Okay, this is final the end of a discussion for synchronous machine. We have discussed on the synchronous generator. Now the other kind of machine we have synchronous application is on the motor. Okay, and we go through the basic principle of the motor and the starting method, Q versus field current of the characteristic of the motor, the voltage curve characteristic, the effect of load changes of the motor, and same per previous motor, the use of motor is to convert electrical power to mechanical power. And we have a motor, we put voltage terminal to the voltage source terminal, so it's end up we shall have a turning on the shaft, and we measure in horsepower, how much the force that we can turn, or we can push, or we can drag the load in terms of mechanical units measurement. So this is the use of your motor. So just that in the synchronous motor, the speed of the shaft can be controlled based on the speed of the induced voltage frequency. So electrically it's identical to the any alternator AC generator. It's the same. For AC alternator, you turn the shaft, you have voltage output. For motor, you put in voltage, you have the turning shaft output, mechanical output. So mostly for synchronous motor, we have the type of salient pole type, and which is the construction will be wider in terms of their construction, and the diameter will be wider, and like this type of motor. Synchronous motor are rated between 150 kilowatts up to 15 megawatt, and run at lower speed, very low speed. Range from 150 RPM, rotation per minute, up to maybe 1800 RPM. So the more poles you put in, you construct, so the lower the speed it will be. So in terms of construction, most of the construction will be like a amortizer windings. We have amortizer winding or damper windings to cater the speed reduction. Later we'll see the speed reduction due to the adding up load to the shaft. So for synchronous motor, the rotor part will be connected to the DC supply. This is your slip ring. This is your DC supply, which will provide the magnetic field. DC supply will energize the pole here to act as permanent magnetic field. And why we use DC supply? Because we can adjust in terms of current that induced into the poles, rotating poles here. If you use we use permanent magnet also can, but we are not able to adjust the amount of the current that flows into the poles. Magnetic field's intensity we can adjust, so means that the producing speed or the power of the motor cannot be adjusted. So that's why we need DC supply, alternating or adjustable DC supply. So basic principles. Synchronous motor construction, design, analysis are very similar to those in synchronous generator. Both are using the same construction concept, except the direction of power flow means that motor will produce mechanical force, generator will produce electrical. So the operation can be found in terms of how much the torque produced by the magnetic fields, and generator how much the voltage, current, power produced. But in terms of motor, how much the torque, the horsepower the shaft can produce. In generator, torque oppose motion, so the rotor flux density must lead the stator flux density. But in motor, the torque is the same direction as motion, so the rotor flux density must lag the stator flux density. And in the synchronous mode generator, the E leads, and the internal generated voltage will lead voltage here. But in a motor, the internal generated voltage will lag the terminal voltage. We put in terminal voltage, we generate the EA. But for synchronous generator, we turn the shaft, we generate EA, internal generated voltage. But in motor, we put in terminal voltage, we produce EA. That's why it lags. Okay, you can see from the graph here. And the same equivalent circuit for motor of synchronous motor. And we have here field current circuit. We have here how much the phase voltage generated to the field. And so V phase equal to how much generated in here, plus the drop, voltage drop at the series impedance, also the series resistance. And internal generated voltage is equal to V phase here minus the drop at your armature. So this one is the armature resistance is neglected. So you don't have here RA, IA. So it remains like S, only XS here. So the torque speed characteristic, and the torque speed characteristic, this is your synchronous speed. This is your zero speed. Zero speed increase to synchronous speed. The pull out torque, the rated torque will be all the same. And at steady state, the speed of synchronous motor is constant from no load all the way up to the maximum pull out torque. The motor can supply, so the speed regulation is 0, because it's not like your induction motor, which the speed will follow the frequency rotation. But for synchronous, the speed will be at the same frequency of your system frequency. So speed is 120 times frequency divided by the number of poles. The lower the number of poles, minimum is 2, so the speed is high. If you put more poles, so the speed will reduce. So the induced torque for 3-phase for equation, this is a load angle values, and delta is your load angle values. So after the motor exceeds the pull out torque, it enters the region of slipping poles. Rotor starts to slip behind, and the lost synchronization means that after synchronous speed, cannot speed more than that, and it will enter the slipping region. And so the speed will be maintained up to synchronous speed, and cannot exceed more than synchronous speed. So in terms of power flow, and so how much P in we put in, we minus how much the internal losses of your copper losses, then minus your losses of your core construction, of how your core being laminated, friction and windage, and the stray losses. So if the armature resistance is significant, the output power at the top of the synchronous motor must be found by the power flow of the machine. So we have here for 3-phase, and mechanical power, we times the horsepower by 746 watt per horsepower, so we get the mechanical power in terms of watts. So the copper loss here, copper loss is 3 times how much per phase we measure the current times the resistance of the phase, times 3. And so I square R times 3. So how much P out we gain from here is the amount of P in minus all the related losses. And the copper loss, rotational loss here. Rotational loss is the amount of stray, mechanical, and core loss. And mix all of them together to become rotational loss. And so this is your output power. So the T out output torque is V out divided by speed, synchronous speed, and this mechanical speed and synchronous speed is the same, so omega s. So in terms of your load current, armature current, load current is the same. Armature current and load current is the same. So P in divided by 3 V terminal cos theta. And this is your load angle. This is your angle between your current and your voltage. So the difference, if we compare between the synchronous generator previously with the synchronous motor, the power flow will be just invert P in to P out. This is P in to P out. And so your equation is almost the same for what being used inside your generator. It's only in terms of power flow is vice versa right now. Okay, the basic principle power factor. As with synchronous generator, armature resistance can often be will not put into account because it has less significant impact and accuracy, so it be neglected. In case of the simplified armature circuit equation, so we can redraw the power factor as per mentioned before above here. This is the simplified leading power factor phasor diagram, the simplified unity power factor phasor diagram, because we have here generated voltage equal to V phase minus armature resistance plus reactance and series reactance. So this is your simplified lagging power factor phasor diagram of your voltage, phase voltage. So we shall see the example, discuss example in later coming slides. So in terms of starting your motor, AC power we apply to the stator armature. We cause rotating magnetic field to the armature around the field. So with the DC excitation current field in the rotor, we generate flux like a bar of magnet. So inside here we have a DC excited current field. So it acts like your permanent magnet. The strong rotating magnetic field attracts and repels the strong rotor field. So you rotate the rotor, you have here internal magnetic field bar. So the attraction will push or pull the bar to follow your external rotating field. So the rotor therefore will able to turn, and it rotates in step with the rotating magnetic field of the armature. So it should work this way once it started, but synchronous motor cannot be started from a standstill by only applying the 3-phase AC power source. Why? Because the direction of instantaneous torque reverse half cycle, therefore it requires a force to accelerate the rotor to the synchronous speed in an instant. So you have to have a rotating field here, 3-phase, then follows by the internal generated bars here to follow the speed.